we seek the forgiveness of Allah. We make sure that we fulfill the duties unto Allah. Many people don't pray during Ramadan. I mean, what's the point? Subhanallah. How can you not pray? How can you miss your prayers during the month of Ramadan? This is a blessed month where Allah wants us to be disciplined. He wants us to gain closeness to Him. لَعَلَّكُمْ تَتَّقُونَ. We've heard that. So Allah wants that for us. It's important that we fulfill our duties unto Allah. Rabbul Izzati wal Jalal subhanahu wa ta'ala. My brothers and sisters, remember that you must fulfill your obligations unto Allah, especially your salah. Also, let's welcome the last 10 nights, wallahi, my brothers and my sisters, by becoming better in the way we dress. In the way we dress. We need to cover appropriately, and then we should try and ensure, according to the teachings of the Prophet Muhammad sallallahu alaihi wasallam, that we wear slightly looser clothing, that we use a material that is not so thin or see-through. And all these are steps towards improvement in our modesty. It's very important because you're not supposed to display your figure in public, male or female. You're not supposed to intentionally, seek that attention upon your body as a believer. That's a teaching of Islam. So yes, you can dress in the most beautiful way, but let it be elegant on one hand, and at the same time, let it be that which is acceptable in the eyes of Allah. Surely we love Allah. Does Allah want you to expose yourself, show your body parts, try and display what you've been endowed with? May Allah subhanahu wa ta'ala make us more conscious of this. So this is a time to revisit the entire wardrobe and see where we can change it for the pleasure of Allah. Or if you have that which is, mashallah, really hot and sexy, make sure that you're wearing it at the appropriate times, with your spouse and so on. And if you're going to be displeasing Allah, it's not worth it. It's really not worth it. And to be honest with you, we must make those changes for the pleasure of Allah. What do we gain? These are the organs. We are taught that the organs themselves will be bearing witness for us or against us on the day of judgment. And this is why the tongue will speak, the feet will speak, the hands will speak. Listen to what Allah says. يوم تشهد عليهم ألسنتهم وأيديهم وأرجلهم بما كانوا يعملون ويكسبون. Allah says, on that day, their hands, their tongues, their hands, their feet will bear witness regarding what they earned or what they did. Now, why would we like those organs to bear witness against us when it was quite easy for us to use the organs in the right direction and to also make sure that they were covered in a way that Allah wanted? May Allah subhanahu wa ta'ala grant us true liberation. Ameen. Ameen, Ya Rabbi. So in the run-up to the last 10 nights, the countdown, we need to make these changes one after the other. It reminds me of a drag race.
Hello? I'm okay, but I'm in class. Good afternoon, everyone.
Good afternoon, sir.
So today we intend to finalize this area of heat. Did people try out some of the numbers? Whenever you don't send numbers, it's evidence that you didn't solve. So when you finish this, next week I will intend to start on fluid mechanics. Okay? Next week, God willing, I start on fluid mechanics. Last time I stopped on which number? Did we do that one? I think we did that one. Did we? That one I think we did. How about this one? That one also we did. Even a cylindrical bulb, I guess we did. Just start, I think, with that solid copper sphere. diameter 20 millimeters, cooled at a temperature of 500 Kelvin, and then is placed in an enclosure maintained at a temperature of 300 Kelvin. Assuming that all the exchange of heat is caused by radiation, calculate the initial rate of temperature fall if the sphere is assumed to emit heat like a black body. Now, we have temperature. Oh, have I showed you the screen already? Sorry, I hadn't shared the screen. This is the shared screen. So we are seeing that we have temperature T1, which is 500 Kelvin. Then we have temperature T2, which is what? 300 Kelvin. Then they are saying, assuming that it is behaving like a black body, remember power radiated? You can recall for us the equation for power radiated. Let me see. Yes, Matov Brian. What is the formula for power radiated by a black body? Merona, what is that power? The power is supposed to be cross-sectional area times what? Stefan's constant times the change in temperature to the power fourth. Some books have it like this: power is equal to A sigma of T minus T naught to the power fourth, where T naught is the temperature of the enclosure. Now, power radiated by a sphere is given by, because power is the rate of change of work done, yet heat is work or is energy. So the rate of transfer of heat is power. So the rate at which heat is being transferred is d2 dt, whereby d2 dt, if you go back to Q, is equal to mc, change in temperature, then d2 dt can be equal to mass is constant, c is constant, theta dt. It is from that reason that power radiated can as well be mc theta dt. So if you confirm that also power radiated is mc d theta dt, then we can equate this mc d theta dt to cross-section area sigma times T to the power 4 minus the temperature of the enclosure to the power 4. And now the question wants us to find the initial rate of temperature fall if the sphere is assumed to emit like a black body. Rate of temperature fall is d2 dt, so we shall have, is d theta dt, the rate of temperature fall. The rate of temperature fall is d theta dt. This is the rate of temperature what? Fall. Whereas d2 dt is the rate of what? Rate of, or is the power radiated by a sphere. Power radiated by a sphere is the rate at which heat leaves the sphere. So therefore, make d theta the subject, d theta dt the subject, which is the rate of temperature fall, from mc d theta dt is equal to cross-sectional area sigma T to the power 4th minus T naught to the power 4th. We shall have d theta dt is equal to A sigma T to the 4th minus T naught to the 4th, all divided by mc. We have the mass. I think we have the mass. We have the specific heat capacity. we must be having a specific capacity of copper. Density of copper was given. They gave us also the diameter of copper. So because they gave us the diameter, we can find the volume, whereby volume is got from what expression of a sphere, 4/3 pi r squared. So this is going to be cross-sectional area times sigma into t to the fourth minus t naught to the fourth. All is over. Mass is density times volume, which is 4/3 pi r to the cube times c. But now cross-section area is also 4 pi r squared sigma of t1 squared minus t2, the fourth, all is over 4/3 pi r cubed rho c. I can vamoosh the 4 pi, the r squared, with 1. Then I'll realize 3 sigma into t1 to the fourth minus t2 to the fourth, all is over r rho c. But r is equal to what? Diameter. R is a half of the diameter, which is 20 times 10 power negative 3 divided by 2, which gives us 1 times 10 power negative 2. We can now substitute. Therefore, the rate of temperature fall will be 3 times Stephan's constant, which is what? 5.67 times 10 to the power negative 8 times 500 power 4 minus 300 power 4, all is over 1 times 10 to the power negative 2 times the density, which is 370, times the specific heat capacity, which is 8930. Press the calc and get the answer. So you see that the concept was just about to know whether you know exactly. Someone is in the chat. Some people need adding. I don't see the adding option. I've added them, I've not seen them. Some of you who joined it, there are some topics you missed in heat. Today I was going through all my videos and I'm trying to upload some of them. Please let me know some of the videos that are missing on my YouTube channel and yet you need them so that I can help you add them. How can I access the notes? The notes I've always been sending them. If there are notes you're missing, just let me know so that I can send them to you. But you can also as well ask people in the group. They have always got notes. But you can also inbox me and I'll be of help. You tell me the area you want, then I see how I can arrange for sending the notes. So are we there? Someone has got an answer of 2.8 times 10 to the power 16. We confirm that. Let's confirm whether that's the answer you're all getting. Okay. People are confirming that that's the answer. We need to get another number. Okay. We have the number of this. Yes, that one. So that's the definition of merging the rate of heat flow as power radiated and merge it as the rate of heat loss due to specific heat capacity, which brings about the rate of temperature fall, is a key relationship which we had to borrow in this question. And some of these other questions that show up. One should be in position to interpret them and relate them correctly. So here we are saying a solar constant, which is the energy arriving per second at the Earth's surface from the sun, is about 1400 watts per meter squared. Estimate the surface temperature of the sun, given that the radius of the sun is assumed to be 7.0 times 10 to the power 5 kilometers, and the distance from the sun to the earth is 1.5 times 10 to the power 8 kilometers, which is the same as 1.5 times 10 to the power 11 meters. And that is exactly the distance from the sun. When we look at gravitational physics, we shall see that as the distance from the sun to the earth. Therefore, if you look at, they have given us Stefan's constant, which is 5.67 times 10 power negative 8 watts per meter squared per Kelvin to the fourth. What else has been given? That is it. So if this is the sun, and this sun of ours, it has an earth. This is our earth that is revolving around the sun, whereby the distance from the center of the earth, the sun, to the earth is the one which has the 1.5 exponent 8, and then the distance from the center of the sun to the surface of the sun is the one which has radius RS. So, if this is where our earth is, then we are going to emit energy within that circumference, within that radius of the earth. So, having converted the radii, we can see that solar constant, remember, Who knows the equation for the solar constant? What is the formula for finding the solar constant? Let me see what's been here. Adnan, what is the formula for finding the solar constant? Yeah? Adnan.
So S.
Eh?
So
No, I want you to first tell me the
that
mathematics.
is S.
The equation statement. Give me the equation statement. Kind of in English, not in the mathematics. Who else can try? Merona failed earlier. Saulo Weapon. Give me the English expression for solar constant.
This is the radius of the sun over radius of the earth squared times Stefan constant, then times the temperature of the sun power 4.
Okay, you have given it to me mathematically. But what I wanted to hear is total energy radiated by the sun out of the area of the imaginary sphere. So I expected this total energy radiated by the sun out of area of the imaginary sphere we are radiating in. So the imaginary sphere is this one. Let me use another color. This is the imaginary sphere where the sun is emitting what? Where the sun is assumed to be emitting its energy. So the total energy radiated is got from cross-sectional area times sigma times temperature of the sun to the power 4 out of the area of the sphere, which is going to be, this is the area of the sun, this is the area of the sphere, area whose radius is big R. So if you substitute, you'll have, because all of them are spheres, we shall have 4 pi small r radius of the sun squared times Stefan's constant times temperature of the sun to the 4th, or is over 4 pi big R squared. So you can divide off the 4 pi with this one, and then this is the reason why our friend stated the equation in this form. This is where the equation comes from to give us radius of the sun squared out of the radius of the earth from the sun squared times Stefan's constant times temperature of the sun to the power 4. This is giving us what we call the solar constant. And according to this question, the solar constant was 1,400. Yeah? This is the solar constant. So therefore, we are looking for the question also estimate the temperature of the sun. So we are making TS the subject. Eh? So TS, the power 4th, can be equal to 1,400 times radius of the sun over radius of the earth from the sun to the square divided by sigma, which is Stefan's constant. And thus temperature of the sun would be the 4th root of all that, which is 1,400 over sigma into radius of the sun over big R to the square. With this, we shall get the 4th root of 1,400 divided by sigma, which is 5.67 times 10 to the power negative 8 into radius of the sun, which is 7.080 times 10 to the power 8 over radius of the earth from the sun, which is 1.5 times 10 to the power 11. All this is squared. Can you press the calculator and get me the answer for temperature of the sun? Sometimes when people hear us talk about temperature of the sun, they say, but physicists are liars. Now, how they know the temperature of the sun? Just tell them we know. It shouldn't, mix you a lot or confuse you at any one time. You just say, we know. Answers, someone has put in the chat. Sir, could you please help me with your number so that I get some information I missed? Okay. 0782 855 674. Someone's getting 27 point. Impossible. The sun cannot even be big. It's less than your temperature, your body temperature. Eh? When you say the answer is 27.079, Matov, the sun to be even less hot than your body temperature, impossible. You check yourself and your calculator. Someone else? 2.0 Saul exponent 12. Saul exponent 12, you've not found the fourth root. Power quarter. Must be getting the answer, you Saul. Power quarter, what answer did you get?
So I've already power quarter.
Ah! That is too much. Are you sure you've already, someone else? Someone else give me an answer. Girls, you're so quiet.
So maybe the radius of the sun here you put to power power 8.
Where?
Here, in the
Until
expression you gave
now,
us.
it was 7.0 times 10 to the power 5. Eh? It was not yet converted. Eh? So you convert it to meters. That's why I put it to 8.
Okay.
Yeah. Girls, all people don't know how to press the color. Another chat has come in. Let's check. I'm also getting 27.09. Ah, are you sure, you guys? Did you square the radius? Okay, let's first handle this one alone. You first handle as 7.0 times 10 to the power 8 over 1.5 times 10 to the power 11. Handle it as squared times 5.67 times 10 to the power negative 8. Then times t of the sun to the power 4. First, get me this side, only this part, and I see the answer you have. Someone else has an answer. I have tried everything, but still 20. Mama Tov, what have you tried? Have you tried what I've said?
Yes.
What answer do you get, okay, when you don't multiply by t at power 4? Well, on the other left-hand side. People, what answer are you getting at this stage? This side. Girls, are you there? Where are the girls? Someone has 0 point. Mama Tovi still have the same wrong answer. Where are the ladies? Namuri, compute this one. There is Namuri. There is the rest. I think I've run away. Namuri, try to compute that and we see. Yeah? 1 more minute for that. Adinani, you have no answer. Merona Muhanji, you've also not responded. I'm wondering, what calculators are you using? So Weapon has brought another answer, 1, 2, 3, 4, 8. That looks like a guess. There are decimals there. How have you removed them? But anyway, the temperature of the sun is a constant. And we know it. You can even check on Google. The sun has around 5,000 Kelvin, close to 6,000, but it's 5,802.74 Kelvin, according to this solution. Check Mr. Google, it's approximately 5,777.67. When they round it off, it's approximately 5,800 still. So the figure is around there. So check yourselves and your calculators again. And no one should say, Mika, I got the answer, but I fear to say it. Some of you might want to brag around. Okay. The last number of this category is here, which is the flux of the solar energy on the Earth's surface is 1.36 exponent 3 watts per meter squared per Kelvin to the 4th. Capture the temperature of the surface of the sun. Now, to start with, we need to know the solar intensity. Who recalls the definition for solar intensity?
Expenditure
Equals R.
Yeah?
Previous number. R for the previous number.
Yeah?
Capital R. What was capital R for the previous number?
What was?
to R from the for the previous number.
Capital R was 1.5 exponent 8 kilometers. So you make it exponent 11 by converting it to meters. So, case one wants the temperature of the surface of the sun. And I was asking people, if you recall the solar intensity, solar intensity can be got from, which is the same as the solar constant. Can get it from pi r squared times sigma t to the power 4 of the sun out of pi big R squared. This will give us when you simplify what you get R squared over big R squared times sigma times temperature to the power 4 of the sun. So the question says find the temperature of the sun. So according to that question, they told us that the flux of the solar energy on the Earth's surface is 1.36. So that was the solar intensity. So this is 1.36 times 10 to the power 3. So making TS the subject to the power 4, we shall have 1.36 times 10 to the power 3. Oh, yes. I know why you're getting wrong answers, guys. You know what I did? When I cross-multiplied this one this way, I did not interchange this one. This was supposed to be R over radius of the sun squared. So can you change that? I did not interchange that. So that's why you are getting wrong answers. Now you're going to brag. Okay. So you change that a little. To 1.5 times 10 to the power 3. Power 11 over 7.0 times 10 to the power 8. I think now the answer comes out. I've seen it when I was trying to make the subject here. So this will become big R out of radius of the sun squared divided by sigma. So this temperature can be found from 4th root of 1.36 out of 5.67 into the radius of the sun, radius of the, I want big R. Big R, was it given? Big R is known. The distance from the sun to the earth is also a constant, 1.5 times 10 to the power 11. Then the radius of the sun itself is 6.96 times 10 to the power 8. Then times, yeah, that's all. But this is raised to the power 2. So what temperature do you get? Someone has a-
5,777.367.
Kelvin. So Bamatov, I think the first one we get this one rightly. Then the second one we're getting what Mr. Google has. So it's approximately the same answers, so no worries. I did interchange the first one. That's why people are getting wrong answers. And no one could see that my algebra got disturbed somewhere. Okay. Then the second question says the power radiated by the sun. Power radiated by the sun is got from cross-sectional area times sigma times temperature to the power 4, which is going to be 4 pi radius of the sun squared times 5.67 times 10 power negative 8 times 577.3 to the power 4. So this will give us 4 times 22 over 7 times radius of the sun 6.96 times 10 to the power 8. But this is going to be squared times 5.67 times 10 to the power negative 8 times 5,777.37 raised to the power 4th. What power is this? What answer did you give? Someone done answer? Someone said an answer. 3.4, 3.4, 3.8. Guys, what answer do you have? 3.8, 3.4. And then power 11 is wrong. Another one. (3.845x by 26), correct. What? Then the last one, they're saying the rate at which the sun is losing mass. You know, when the sun is burning, it loses some mass. Now, according to energy from Albert Einstein's mass energy relationship, E is equal to mc squared. So the rate of change of energy is power. So this is going to be the rate of change of mass with time, mc squared, because c is the constant. So this is the same as c squared dm dt. We are looking for the rate at which mass is lost. And because this is equal to dE dt is power, so this is equal to P. Therefore, dm dt will give us P out of c squared. So can we substitute? The power we have got is 3.84 times 10 power 26 divided by 3 times 10 to the power 8. All of this is squared. What is the rate of mass loss?
One 1.6384 exponent 36.
What?
Sorry. No, sorry.
Wrong.
4.2667 exponent 9.
These are kgs per second loss. Correct. So we have the last definition, which is called the intensity of the solar radiation, which I wanted us to finalize with today, that we have taken along with examples here, because learners never tried any. Oh, they are done. So we are saying you're looking at intensity of solar radiation at the Earth's surface. Intensity of solar radiation at the Earth's surface. So the intensity of the radiation from the sun, we have been calling it the solar constant, and is given by from the definition of the solar constant. We saw the solar constant was equal to power radiated by the sun, which is 4 pi radius of the sun squared times sigma times temperature of the sun to the power 4 divided by the area of the sphere which receives the radiation. And this was confirming that radius of the sun out of the radius of the sphere squared times sigma times temperature of the sun to the power of 4 gives us what we call the solar constant. Now, how about the solar power received by this Earth? The solar power received by the Earth, solar power received by the Earth is equal to the solar constant. Because solar constant is power over area, it will be the solar constant times the area of the Earth's cross-section, times the cross-section area of the Earth, whereby power received by the Earth is going to be PE, which is going to be the cross-section area of the Earth is pi radius of the Earth squared times radius of the sun out of radius of the sphere of emission of the sun's power times Stefan's constant times the temperature of the sun to the power of 4. So we can also note that when the Earth is in radiative, radiative, not radiactive, radiative equilibrium. When I say radiactive, I mean radioactivity. But when I say radiative, we are talking about radiation of the power. When it is in radiative equilibrium, what happens? It means the power received by the Earth is equal to power radiated by the Earth. Power received by the Earth is equal to power that has been radiated by the Earth. This is when we say it is in radiative equilibrium. So in that sense, we shall have power received by the Earth is cross-section area of the Earth squared times radius of the sun out of the radius of the sphere emitted by the sun times Stefan's constant times temperature of the 4th is equal to power radiated by the sun, by the Earth, which is going to be 4 pi r e squared sigma temperature of the Earth now, not temperature of the sun. Yeah. So the power received by the Earth is actually equal to the power radiated by the Earth if we say the Earth is in a radiative equilibrium. And we have seen the equation for power received by the Earth, and we can also predict the power radiated by the Earth. Because just like we have been seeing, power radiated by the sun is the area of the sun, which is the area of the sphere of the sun, times the Stefan's constant, times the temperature of the sun. But now, we shall say it is the area of the surface of the Earth, which is 4 pi r of the Earth squared, times Stefan's constant, times temperature of the Earth to the power 4. With this, we can simplify and we can find the value of the temperature of the Earth. The temperature of the Earth can be got from pi, radius of the Earth to the square, times r of the sun out of radius of emission of the sun to the square, times Stefan's constant, times the temperature of this was temperature of the sun, times temperature of the sun to the power 4, all divided by 4 pi radius of the Earth to the square times Stefan's constant. And with this, I'll vamoosh that. With that, I'll also vamoosh the following, which is Stefan's constant. We'll go off with that one by dividing them, and we get 1. So therefore, the temperature of the Earth to the power 4 can be got from 1/4 the temperature of the sun to the power 4. With this n times what? Radius of the sun over radius of the sphere where the sun has emitted its power to the square. So if one wants to get the final temperature T of the Earth, then it's going to be 1/4 into RS over big R to the square times the temperature of the sun to the power fourth, but all this being raised to the power a quarter. This is the expression for the temperature of the earth, where RE is the radius of the earth, TE is the average temperature of the earth. Just like also the earth, also other planets are radiative. So the earth and other planets radiate as a sphere. Meanwhile, they receive radiation from the sun as a circle. You know why we say they receive radiation from the sun as a circle? Because when we are talking about power received, we use the area of a circle for the earth. It is because, let me use another illustration. It is because when you look at an illustration for our earth, assuming this is our earth, right? You've all known the earth for some good time. And then this is our sun right here, right? If we all know that that is our sun, when radiation comes from the sun, comes and strikes the earth, it will leave the sun and come and strike the earth. When it strikes the earth, a given percentage of the earth will actually experience the what? Will actually experience the radiation. So when you look at it, it will have experienced radiation in this form. It will have been a circular patch. If you're on the sun, you would see a circular patch on the earth that is receiving the radiation. So behind this way, we are not receiving radiation. Behind this way, it is night. For us now, we are here during the day. We are receiving radiation from the sun, but we receive it as a circular patch, because not all the surface of the earth at any one time is receiving the entire energy from the sun. Not all the earth at any one time is having sunlight. I think you know that right now, for example, in US, they are asleep. Very asleep, deep asleep. They are really like with around 4 hours to wake up. Very sleepy, very snoring. Canada, they are snoring. Alaska, very busy, snoring. But in Uganda, we are enjoying life. We are enjoying Zoom classes. I used to have a Zoom class with some students of GS in USA. But in actual sense for them, actually, no, it is still very early. It has just become dark in their country. No, it is dark. They are going to wake up. So you could see that I could teach them at around 11 p.m., midnight. That is when it is around 9 a.m. Around 9, around 10. So sometimes they could wait. I doze off also, as the mother tells me, wait, they are still asleep. I have to wake them up, you know? So it is not possible for the earth to have the entire globe that it is daylight. It is impossible. Even if we get closer, to the sun like a year, still this side will be light, this side will be dark. So the surface which will be receiving sunlight will still be, receiving sunlight will be what? Will be circular. So that is why we assume the earth receives the sun rays or radiation in a circular form. That is the reason why we use pi r squared. Then when emitting, it emits as a whole of the earth. So it emits like a sphere. So it emits in all directions when emitting. That's why when emitting, here we are using 4 pi radius of the earth squared. Then on receiving, we are receiving as pi r e squared. Is that message very clear? Okay, let's have an example. If no questions. Let me send one example here. Yes, anyone the question? So we have an example here. Estimate the temperature of the Earth, assuming that it is in radiative equilibrium with the sun. Radius of the sun has been given. Radius of the sun is equal to 7.0 times 10 to the power 8 kilometers. Temperature of the sun has been given as 6,000 Kelvin. Distance of the sun from the Earth, big R, has been given as 1.5 times 10 to the power 11 meters. But we have seen that at radiative equilibrium, that is at equilibrium, power received by the Earth, this is the equation statement. Power received by the Earth is equal to power done what? Radiated by the Earth. If you recall, when power is received by the Earth, we receive it by pi r e squared of radius of the sun out of radius of emission of the sun squared times temperature of the sun to the power 4 is equal to 4 pi radius of the Earth squared times Stefan's constant times temperature of the Earth to power 4. So because we are estimating the temperature of the Earth, we shall have the pi can die off. We can reduce the radius of the Earth, and we can get a quarter radius of the sun out of radius of the emission of the sun to the square times temperature of the sun to the power 4. Can we substitute now and get the answer? Temperature of the Earth to the 4th will give us a quarter into brackets. Radius of the sun is 7.0 times 10 to the power 8, all is over 1.5 times 10 to the power 11, all this raised to the square times 6,000 to the power 4. Calculator, what is the temperature of the Earth? So that temperature of the Earth is assumed to be the average, including all the cold regions, the very hot regions, the deserts, the waters, the temperatures we have in all those places. When you get their average, you get an average which is even less than 20 degrees. But sometimes you feel like, my God, the sun is too much here, it's around 40. Sometimes you feel that when the coldness is too much, it may be around what? Around 10 degrees, but it is rare. For us to be at 10 degrees, all of us can be shivering all the time. Yes, what answer you get?
Teacher, I was asking whether the radius of the sun should also be in meters.
Everything is supposed to be in meters. We work in SI units.
But you've written it as 7.0 exponent 8.
It was exponent 5 in kilometers. Hey, sorry. This was in meters. Eh? Check this out. Okay, they were in meters. I think you are ready for a test now in heat. Your test will be for 3 numbers of heat because we are done with the topic, with the section. The entire section of heat is finished. So we are done with it. I can give you a set of questions for you to try out. The second number, you're going to do it. I've sent it on the WhatsApp group. And the answers for that second number are, this is the second number. These are the answers. Either you screenshot them or you take them down. The solar constant for Venus, the answer is 2664.73 watts per meter squared. Then the temperature The equilibrium temperature of Venus, assuming it absorbs and radiates like a black body, is 56.23 degrees Celsius or 329.23 Kelvin. So what temperature do we have for the Earth?
289.83.
Subtract off 273 to convert to degrees Celsius.
$16.83.
Very good. 16.8 degrees. So whenever you check a given area, which is 25 and above, which is 16.8 and above, those areas are a little bit warmer compared to the Earth's average. So Uganda, it's a warm country. Though we sometimes experience some temperatures below 20. Like the other time it was very cold. I think when yesterday it was very cold. When you experience very cold temperatures, we just slightly go below 20. But in most cases, we are above 20. We are 21, 22. When it's so hot, 29, 27. There we are feeling so hot. But if you go to the desert, my God, those guys reach 40. Yeah? For them, their temperature reaches there. Then if you go to cold regions, when people are in winter, it is very cold. The temperatures are below 10. Now, as winters, there is what we call spring, then there is what they call winter, there is what they call summer. I think spring is what comes either before or after snow. I'm not sure, but something like that. A season close to snow. It is a very cold season. You know, snow forms ice. So if it's a very cold season, that season can be slightly above 0 or it's below 10. Then when it reaches 0 degrees, freezing starts. So the rivers can freeze, some ponds and swamps can freeze. Then there are some regions which go to -5, -10. Look, I think, was it last year, the other year? I think 2019. Their winter went up to what, July, and they were shocked. Up to July, May. It came from December. Winter stayed for 6 months, almost 6 months. There is a problem if something like that happens. Even us nowadays, you know, it has been a problem. All this time, we all knew that in August, from August up to December, it's raining. And guess what? The rain has not been showing up. It has just started in October. More so when you're almost halfway. So it means there's a problem with the atmosphere. There's a problem with how the rains are made. And that is being caused mainly by us. So with that regard, we have seen how the average temperature of the Earth can be found. And the last method of transfer of heat is convection. Those convections, I'm going to send them the note. I'm going to send you the notes. They are not so much of a complication. Convection as a means of heat transfer in fluids, which is the actual movement of fluid molecules. They are just the examples are land and sea breezes, which you have seen in your O level. And I trust you can discuss them. Then I'll also send some more 5 numbers to look at in your free time. And that is marking the end of heat and thermodynamics. Congratulations to all of you who have been with us from the beginning. You are lucky. You have finished the syllabus of section B of paper 1. You are left with only 2 sections. But as we speak, it means if you have been a serious candidate, you should be in position to do 2 numbers from this section now. Unless when I finish other sections, then you can say, but this section is better, then you can do other 2 from elsewhere. But don't be a mean student who will say, I'll do only 1 because of, I feel like I don't want heat so much. As per now, what we are at, all of you are capable of doing 2 numbers if you have been serious and active. Okay, with that, allow me to stop there. Our time is up. We hope to meet next week again. Like I've said, next week I'm introducing a new item, a new element. It looks like a new item, or it looks like a new section, but it's not a section. It's a section within a section. That is fluid mechanics, mechanics of fluids. Yeah. So I will start from the beginning, which is hydrostatics and Archimedes principles. Then we go all the way, viscosity, all the way, Bernoulli's principle, all the way, surface energy, all the way to capillarity, until we finalize everything concerning fluid mechanics. Fluid mechanics was differentiated from the other mechanics you have. So fluid mechanics is not taught in math, but the rest of the mechanics we have, apart from gravitation, is taught in mathematics. Though some not in detail, like we do in math. In math, we don't do so much details of the words. In physics, we do a lot of details of the wordings and explanations, while in math, we do a lot of details of calculations. So fluid mechanics is not anywhere in mathematics. Those who intend to say, we cover them in math. Just like we have COG in math, we don't have COG in physics. But the rest of the topics are there. We have elasticity, we have circular motion, we have supermonic motion, we have equilibrium of forces, we have resolution of forces, we have projectiles, we have even dimensions are not there in math, but they are there in physics. So those are the differences. So this one, we have fluid mechanics, we don't have it here in math. So find means of attending, and we'll be in position to also cover that very fast. I pray that by the end of the year, I will have finished modern physics, and I will have finished some good mechanics on the other side. Just like I'm praying that I will have finished mathematics mechanics, just like I'm finalizing with START, then we shall sober out with pure math until the end. Okay, with such information, we have a very good evening. In case of any other questions, inbox me. I can always be of help.